now are going to turn our attention to polynomial functions. In order to understand them, we need to know what a polynomial is. And a polynomial expression can have constants, like the number 4, variables like x or y, and exponents, like the 2 and y squared, that can be combined using addition, subtraction, multiplication, and division, but it can't include division by a variable. A variable's exponents must be whole numbers. Okay, so the numbers starting at 0, 1, 2, 3, and so forth. No decimals, no fractions, no negative. There can't be an infinite number of terms. So let's take a look at a few examples. This would be a polynomial. All the exponents are whole numbers, and we don't have division by a variable. Same is true for this one and this one. Even though it's simple, it's still considered a polynomial. In fact, it's called a monomial. And this one. 2x to the 1/2 power would not be a polynomial because it has a fractional exponent. 3 times the square root of x plus 1 would not be a polynomial because the square root symbol is equivalent to a 1/2 exponent. And if you haven't seen that before, that is something you will learn. But for the time being, just know that if you have variables under a square root, that will not be a polynomial. This example is not a polynomial because of the -2 on the x. You must use only positive whole numbers. And this one is not a polynomial because we do have division by a variable. Notice that below the fraction bar, we have x squared plus 4. That's saying we would be dividing by x squared plus 4, not a polynomial. What are polynomial functions going to look like? They're very well behaved. They're smooth, continuous curves, or as you see in the case of f of x equals -3, a constant function is also technically a type of polynomial. It's a polynomial where the variable has an exponent of 0. In each case, I could trace the graph starting at the left all the way to the right and never need to lift up my pencil. That's what continuous means. Here are some examples of things that will not be polynomial functions. They might have sharp corners, like h of x equals the absolute value of x plus 2, where there's a corner at -2. Also, h of x equals x to the 4/5 power. It has a cusp happening at 0. Anything with a break in the graph or a discontinuity will not be a polynomial function. In the case of h of x equals the square root of x plus 1 minus 1, we have a discontinuity happening. The graph stops at -1, -1, and does not continue. And lastly, we have the rational function h of x equals x plus 3 divided by x minus 1. You can see we've got that division by a variable. And we have an infinite discontinuity in this case because there would be a vertical asymptote happening at x equals 1. Now some vocabulary. The degree of a polynomial is the highest exponent that appears on a variable. So if you look at our first polynomial f of x, you scan the exponents. The highest exponent on the variable is 4. So we say that's a polynomial of degree 4. Now in the second example, the terms are mixed up. They're not arranged in order of exponents, but when you're looking for degree, you still look for the highest. The highest exponent is the 5 on x to the 5th. So this is a degree 5 polynomial. The leading coefficient of a polynomial is the coefficient of the variable with the highest exponent. So first, you scan the polynomial and find the highest exponent. In the first example, you can see we have an x to the 4th. Then you look at the coefficient of that term. In front of the x to the 4th is a -6. -6 is the leading coefficient. Now, if your polynomial, like in the next example, is sort of out of order, you still go to the highest exponent term first, which is the -7x to the 5th at the end. You look at what's in front of the x to the 5th, which is the -7, and that's the leading coefficient. Now, the reason we care about degree and leading coefficient is it tells us something about how the graphs are going to behave. Here you can see a picture of different types of polynomial functions. Linear functions are technically polynomial functions with a degree of 1 because they're going to have that format y equals mx plus b, and x is to the first power. We just finished looking at quadratic functions where x will always have a power of 2 on it. Cubic equations are what we call a degree 3 polynomial. Quartic is degree 4, and quintic is degree 5. And what you want to observe is that the end behavior, literally what the ends of the graph are doing, is the same for even degree functions and odd degree functions. What I mean by that is when you look at the degree 2 and degree 4, you're going to notice the ends, the arrows, are pointing in the same direction. Both of these are pointing up, but it is a possibility they could also both be pointing down. When you look at the odd degree functions, 1, 3, and 5, you're going to notice the ends are going in opposite directions. One of them is down, one of them is up. And it doesn't matter which is which as far as being the left end up or down, right end up or down. There just need to be opposites. And we can predict what that end behavior is going to be knowing two things about the polynomial: knowing its degree and its leading coefficient. This process is called the leading coefficient test. As this summary shows you, if your degree is odd, but your leading coefficient is positive, a greater than 0, your graph will have a left end pointing down and a right end pointing up. If your degree is odd, but your leading coefficient is negative, the left end is going to be going up and the right end is going to be going down. So notice, odd functions have end behavior that goes in opposite directions. For even functions, if your leading coefficient is positive, both ends are going to point up, and we saw this with quadratic equations. If your degree is even, but your leading coefficient is negative, remember that's like the frown parabola, both ends are going to point down. Here's an example of how you would perform the leading coefficient test. Which of the following polynomials will have a left end that falls and a right end that rises? Visually, that means we're looking for something like this. Left end pointing down, something happens in the middle, and the right end ends up pointing up. The first helpful thing to do is identify the degree of each polynomial. The first choice has a degree of 2, so it's even. Below that, we have an odd degree, degree 3. F of x equals 8x plus 3 is odd degree because if there is no exponent on the x, it's assumed to be a 1. And the last f of x equals x to the fourth plus 3x has a degree of 4, so it's even degree. That alone tells us something. The polynomials that are even degree have to have ends going in the same direction, either both up or both down. So I can immediately eliminate those options. Now for the odd degree, they do have ends that go in opposite directions. The question is just which one is left end down, right end up. If you look at f of x equals negative 2x cubed plus 5x squared, you now look at its leading coefficient. The leading coefficient is negative 2. Because it's negative, the graph as a whole is going to slope downward. So the first graph is not what this polynomial looks like. It's going to look like the second graph, except we don't want that. That leaves us down to one choice, which is f of x equals 8x plus 3. It does turn out that this is the correct choice. The leading coefficient, the coefficient of the x to the first, is 8. Because that is a positive number, the graph overall is going to be increasing. The left end will be pointed down, the right end will be pointed up. Okay, and now just a couple of my MATLAB examples. Question 1 says, determine if the following function is a polynomial function. If it is, identify the degree. When I look at this polynomial, the thing I notice right away is that I have a fractional exponent on the variable. This is not allowed in polynomial functions. Therefore, this one is not a polynomial. In number 2, we see an example of something that is a polynomial. All whole number exponents and no division by a variable. Question 2 says, use the leading coefficient test to determine the end behavior of the graph of the given polynomial function. Choose the correct answer below. In order to apply the leading coefficient test, you need to know two things. You need the degree and you need the leading coefficient. The degree of this polynomial is the highest exponent that appears, which is 4. The leading coefficient is the coefficient of that highest degree term, and the number in front of the x to the fourth is -5. So my leading coefficient is negative. Because this is an even degree polynomial, the ends need to go in the same direction. So the ends will either both point up or both point down. I can immediately eliminate choice A, and I can eliminate choice D, because both of these have ends going in opposite directions. So I'm left to choose between either both ends are rising or both ends are falling. When you have a negative leading coefficient, like we saw with quadratic functions, both ends are going to be pointing down. Therefore, we would not choose B. The correct answer is C. And one final question for you. Question 4 says, write a polynomial function that imitates the end behavior of the graph shown to the right. The dashed portion of the graph indicates that you should focus only on imitating the left and right behavior of the graph and can be flexible about what occurs between the left and right ends. If we look at our graph, we see that the ends are going in the same direction. This behavior is true of polynomials of even degree. So if I look at my choices, the degree of the first choice is 6, which is even. Second choice is 7, so I'm going to eliminate that option. Third choice has degree 5, which is odd. Eliminate that option. And the fourth choice is again even. So I've narrowed myself down to 2 choices. When both ends point down, that tells us that the leading coefficient will be negative. If the ends pointed up, then we know that the leading coefficient was positive. In this instance, I'm looking at the first situation, so I need to choose the choice that has a negative leading coefficient. I look in front of the x to the 6th, and I see it's a -7, which means this will be the correct choice. The last choice, when I look in front of the x squared, is a +11, and therefore can't be correct.